Hello everyone, welcome to Unit 1 Lesson 6 for Computer Science Principles, where today we're going to be talking about how to represent text in computer science. So for today's lesson, if we go on over to Google Classroom, here we are in Google Classroom. For Lesson 6 we have two items. We have our PowerPoint presentation that I'll be guiding you through today, and I also have the student deck here. So go ahead and download the student deck PowerPoint presentation, and this will look like this. And this is what this is what you guys are going to populate and complete as we're working through the presentation together. So let's continue on then. Unit 1, Lesson 6, representing text. So warm up for today. So we have a list of numbers here, 1, 1, 2, 14, 7, 4, 10, 31. What do you think this list represents? So and here's a hint for you. Pay attention to the format of the list. So we have a number in a space and another number. And in all cases, that's what it looks like. 1, 1, 2, 14, 7, 4, 10, 31. So I'm going to give you just a minute to see if you can figure out what that list represents. And go ahead and pause if you want to take a couple of minutes longer. So what do we think this list represents then? Let's go over to our student deck here. 1, 1, 2, 14, 7, 4, 10, 31. What do you think this list represents? So you may or may not have figured out these are public holidays, and I'm going to say in the US because some of these are not observed elsewhere outside of the US. So we got 1/1 January 1st, 2/14 February 14th. Not sure what that is. I'd have to take a look at the calendar for that. February 14th is Veterans Day. I should have known that. February the 14th, Veterans Day. 7/4, July 4th. And 10/31 is October 31st. What is that one? That is Halloween. I guess that isn't a public holiday, but okay, let's say rather than public holidays, then we'll just say these are events that are celebrated. I know Halloween is a pretty big event here in the US, so we'll give it that. So basically, what we're looking at here is a list of dates, and we've represented them using numbers. So let's go back to our presentation here. All right. So for today's activity, go ahead and take a look at these three text samples here. Hey, TTYN, TTYL. So I'm sure you all know means, or it's an acronym for talk to you later, and morning. So look at the sample text on the screen here. Using only numbers, you will need to represent these samples. No letters or characters allowed. Come up with a system that allows you to do this. So if we look back at the previous slide here, where we used our where we determined this was dates, we've used numbers here to represent the day in the month. So we want to use something similar. So using only numbers, we need to represent these textual samples. So go ahead and think about how you would do that for a minute. And then once you've thought about how you might like to represent those text samples using numbers, we can continue on. So go ahead and pause, and then figure out how you want to do that, and then unpause, and we'll continue on. Okay, so on our next slide here in the student deck, we have our textual samples here. And then we're going to write down a system that allows you to communicate the above message using only numbers. So, so what would our system be? I'm sure that you've probably thought of a system that looks something like A equals 1. equals 1, B, can't type today, B equals 2, C equals 3, and so on and so forth. So since H is the A, B, C, D, E, F, G, H, 5, 8th letter of the alphabet, we're going to say Hey equals 8, and E is A, B, C, D, E, that's the 5th letter, and Y is going to be 25. 8, 5, 25. And we're going to have to format those in a manner where you can see that we have 2 single-digit numbers followed by a double-digit number. There's a couple of ways you can do that. You could put spaces in there, or you could make all your numbers 2 digits just by putting a 0 in front of it. And that way, where did I just do that? 25. There we go. So 08, 05, 25. And then TTYL and morning. I'm not going to do the same. I'm not going to determine what those are in numerics, but following the same system, you can figure out what those would look like. And I'm sure you've all come up with a system fairly similar. You may not have started with 1, you may have started with a higher number, you may have started with 0. You're computer scientists, and we spoke about this before. Computer scientists do like to start with 0, so you may have started with A equals 0, B equals 1, C equals 2. So continuing on. Challenge 1. Use your system to write the message, oh no. Now straight away, you can see here that we've gained something that my previous system hasn't accounted for. We have a space here in the middle of the text. So how do we represent a space for me? Or how would you represent a space using your system? So go ahead and move to slide 2 and determine how you would communicate that with your system, and describe whether or not you are able to communicate that message exactly using your system. Go ahead and do those 2 tasks, and then come back. Go ahead, pause, and then come back once you have completed that. Okay, so use a system from previous slide to communicate the message above. So for me, it would be A, B, C, D, E, F, G, H, I, J, K, L, M, N, N. O is 16. So it would be 16. H, A, B, C, D, E, F, G, H, 5, 8. 08. And then somehow I've got to represent a space here. So I'm going to skip the space for now. I'm just going to go on and say no. N is A, B, C, D, E, F, G, H, I, J, K, L, M, N. It's 14. And then we know O is 16. So how am I going to deal with this character space here? Well, there are, let's say, are you able to communicate the message exactly? No, did not. Did not account for the space. So let's take to the next slide. To do this, update your system if needed. So from slide 2, this is what my system is. Yep. I want to paste my system in here. And then I'm going to say space equals 0. And then I can represent my oh no now by saying there we go. So 16 is O, and 16 is O, 8 is H, 0, 0 is space, 14 is N, 16 is O. So that's how I'm going to take into account space. So, challenge number 2, use your system to write the message great. Well, I can see more issues here. I can see 2 issues here. Go ahead and pause for a minute, see if you can figure out what those issues are and how we might think about how to accommodate them. Okay, so the 2 issues we can see here are we now have capitals as well as an exclamation mark. So we've now got special characters. We've got uppercase characters, we've got lowercase characters, and we have special characters. So if I go over to the next challenge here, using only the numbers in your updated system, how do you communicate the following message? Great. Well, I can't because I don't have a number to represent a capital G, and I don't have a number to represent the exclamation mark either. So I can do the R, E, A, and T, but it means it's not complete. So are you able to communicate the above message exactly? No, did not count for uppers or specials. So update your system. So what are we going to do to update our system to allow us to account for both uppercase characters, lowercase characters, and special characters? So go ahead and pause here for a minute and update your system, and then once you have your system updated, come back and then continue on. Alright, so what was my system from before? This is my system from before. Now, I need to make a change here. So D, E, F, G, H, I, J, K, L, M, N. No, it's not going to work, is it? Let's do it. That's all right. Let's do it this way. Yeah, this is probably easier. So I'm going to say A, B, no, C, D, E, F, G, H, I, J, I, J, K, L, L, M, N, O, P, Q, P, Q, R, S, T, U, stop it, V, W, X, Y, and Z. Okay. And then underneath we can say 0, 1, 2, 2, 2, 3, 2, 4, 2, 5, 0, 6. Right, let's just infer the zeros. So we'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we need to try and line these up. actually. Let's do this. So while you're trying to do your system here, what I recommend is change your font. Change it to Korean New, because it puts all the characters the same width as each other. It's not spaced out. So it's like old typewriter font. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. U, V, W, X, Y, Z. Okay, so 1 to 26 is lowercase. And then we can say B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. So let's start at 27. So we'll say 27, and I'm going to change the font again here, make it easier to. There we go. 27. Now 28. Probably going to run out of space on the width here. Oh, look at that, just enough. Right, 27, 28, 29, 30, 31, 5, 6, 37, 39, 40, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, and 52. Alright, so I've got my lowercase ABCs, my uppercase ABCs, and then we need special characters. So just going across the top row of the numerical keyboard, the shift and number keys across the top of your keyboard. What have we got? We've got exclamation, we've got an @ sign, we've got a pound sign, $sign, %, circumflex, is that called? I'm not sure. Ampersand, asterisks, open parenthesis, close parenthesis. Alright, so need to give these numeric values. And it's still in Korean use, it's fine. So 53 would be next one. 53, 54, 55, 56, 57, 58, 59, 60, 61, and 62. Alright, so here we have my uppercase, my lowercase, and my specials all mapped out. So now I can represent great because I've access to uppercase, I've got access to lowercase, and I've got access to specials. Okay, so that was challenge number 2 completed. Let's take a look at challenge number 3. So what have we got in here? Well, we've got, like we had before, uppercase characters, we've got lowercase characters. I forgot to add my space to my system here. So let's say space equals 0. Alright, so we've got numbers now, so we have to deal with numbers. So go ahead, see if you can use the numbers that you've already developed in your system to communicate the following message. 3 at 5. And as I already pointed out, and I'm sure you've already seen and realized, since we have a number 5 in there, we're not going to be able to do that. So you're going to be able to do everything 3 at and the exclamation mark and the question mark, but how are we going to get 5 in there? In fact, we can't even put the question mark in there because I only did special characters up to the top row of the number keyboard. So let's put a question mark in there. I'll have to call that one 63. So in order to do a 3 at 5, we can't because we did not take numbers into account. So go ahead and shoot to the next slide here. So copy your completed updated system from slide 6 and make any additions or modifications necessary. So go ahead and copy out whatever it was you put in slide 6. And we're going to put it here in slide 8. And then go ahead and figure out what you need to do to include numbers in there. Pause and then come back once you've added that to your system. Okay, so let's go and add numbers to the system here. So we want to start at 0 because we'll have to, let me change my font here again, Times New Korean New. So 0, 1, I wish we could do that, 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. So question for you while I'm doing this, we have our numbers 0 through 9. Do you think we need to continue? Do we need to continue this number indefinitely? So do I need to go to 10 and 11 and 12? I would suggest not, because 10 is made up of 1 and a 0, 11 is made up of a 1 and a 1, and 12 is made up of a 1 and a 2. So we'll go to 0 to 9. And then we'll start counting at 64. So 64, 65, 66, 67, 68, 69, 70, 71, 72, and 73. Okay, so this is my system now. I have uppercase, I have no lowercase, I have specials, and I have numerics. So now I can represent 3 at 5 because I have access to all of those. So challenge number 4. Use your system to write the message, "See you tonight." Well, I don't see anything in there that we are missing from the previous challenge, or from the previous system. So if you have also got everything covered, then go ahead and enter here what that would look like, and explain if you are able to communicate the message exactly. And for me, it's a yes, because I covered every single character that we could have used, that we would have needed to use here. So go ahead, enter your updated, enter the value of what "See You Tonight" will look like in numbers. If you are missing something, then go ahead and update your system to account for it, and then go ahead and put your values in here. And I'll give you a couple of minutes to go ahead and take a look at doing that. Pause, and then just come back when you're ready. Okay, so what did you guys just do? You guys invented a system for representing text in computer systems using numbers only. Now, it was kind of an academic exercise because we already have a system for this, and it's called ASCII, the American Standard Code for Information Interchange. It's used worldwide. I mean, there are a couple of very similar standards. Another standard is called ANSI, but ASCII is the main one. And what you can see here is an ASCII table. We are starting at number 32, and we are going all the way up to number 126. And these are all of the characters that the ASCII table can support, or that the ASCII system can support. And if you think about word processors, things like Microsoft Word from, things that predate Microsoft Word, those are all of the characters that were ever supported. So if you look at the really old non-graphical word processing applications from like the 80s, these are the only characters you would have ever been able to type in there because it only supported ASCII. So like you said, we started precision 32, and that's a space. So ASCII 32 is a space. ASCII 33 is an exclamation, and we've included some characters that I didn't include in my system, all the way up to our tilde at 126. So prompt here, what is the system? What's the same as the system you created? Well, for me, it's similar. I started off with my lowercase characters first, but I increased it 1 as I got up to Z, and then I added a space, and then I added uppercase characters, which I added afterwards. They had higher values than what they do in this ASCII table, but for the most part, it's very similar. What is different? Well, we're starting at 32 instead of 0, so I guess that's the biggest difference here. And what is the most interesting or surprising about the system is probably for me is that it does start at 32 and not 0. Now there is a reason for that, and I can't remember what that reason is right now, so I would have you go ahead and Google that. So Google, why do we start ASCII characters at position 32? In fact, let's go check it out. Let's go to Google. Why does ASCII start at 32? So the first 32 codes, numbers 0 to 31, are for control characters. So codes originally intended not to represent printable information, but rather to control devices such as printers that make use of ASCII, or to provide meta information about data streams such as those stored on magnetic tape. So if you think of the F keys across the top of your keyboard, I don't have any here on my Mac, but for those of you who are using a Windows device or an older Mac, you can see we have F keys across the top. Those F keys typically would have gone much higher than F12 if you look at really old computer systems. Mainframe terminals, things like that, those numbers would have gone probably way up to like 30, 31. So those are special control commands that could be used to send values to peripherals. So things like printers, or like it said here, printers, or being able to control things like magnetic tape drives, something like that. So that's why we start at 32. Okay, so let's go back to our student deck here. Oh, yikes. So what's the maximum number of bits each of your system would need per character? How do you know? And a hint here, convert your largest number. So this is using your system, not using the ASCII system. So this is using your system. Convert your largest number in your system into binary. How many bits does this number require? Well, for me, my largest number is 73. So what is 73 in binary? I'm going to cheat and see if Google can convert that for me. 73 in binary. Decimal to binary. 73 to binary. That didn't work. Oh, I guess here it is. 1, 2, 4, 8, 16, 32, 64. So it did convert it for us. So 1001,001. So that is that's the binary version of 73. How many bits is that? So that's 1, 2, 3, 4, 5, 6. So that's 7 bits. So for me, going back to here, what's the minimum number of bits each of your system would need per character? How do you know? Convert your largest number in your system into binary. How many bits does this number require? So for me, 7 bits. 7 bits. And if we take a look at the ASCII code page, just out of interest here, the highest number here is 1, 2, 3, 4, 5, 6, 7. 7 bits as well. So we build everything out into 8 bits, which is a byte. Remember we spoke about representing binary numbers and that 8 bits is a byte. Well, every character is a byte. So if you have a string with 5 characters in there, you'll know that that string contains 5 bytes of data. We don't use all of the bytes in there. We don't use all of the bits in there, but we do use the entire byte to represent the character. So although it's only 7 bits, it's really 8. 8 bits is 1 byte. 8 bits is 1 character. 1 byte is 1 character. So although it's 7 bits, ASCII table, when we talk about how when we actually use that, we say it's 1 byte is 1 character. So moving on. So you just invented your own scheme for representing text with numbers. Given we use text on our phones and computers all the time, we should assume that there is a standard representation of most of the symbols you can type on an American keyboard. And it's not just an American keyboard. Well, no, I'll take that back. The ASCII code was developed for an American keyboard. There are symbols that you would find on non-American keyboards that are not in that standard ASCII code page. For instance, one of them, important for me because I'm from England originally, is the British pound sign. So the British pound sign is not listed in the standard ASCII code page. $sign is. It is here, ASCII 36, but we don't have a British pound sign. And then likewise over in Europe where they use the euro, that was a new symbol that was added. I think it's like Alt and 4 on a European keyboard. We don't have that in the ASCII code page either. So here we go, the ASCII code page, pronounced ASCII, or the American Standard Code for Information Interchange. Nobody calls it the American Standard Code for Information Interchange. Just call it ASCII. And we have the ASCII reference sheet in the PowerPoint deck. We spoke about those. So what is the same as the systems you created? These are the same prompts that we spoke about here. So like I said, very similar. What's different? Not a whole lot. And what's the most interesting and surprising? That it starts at 32 rather than 0. So representing text is an example of abstraction, which is when we create simplified representations of something more complex. So if we go back to our PowerPoint presentation here, here's an example of abstraction. We have a text. So you got your iPhone here. We can tell it's an iPhone because it's an old iPhone actually, because it doesn't have the Face ID on there. It has a fingerprint reader. So anyway, that's an iPhone. We send a text to our friend here saying, how's it going? We're abstracted from anything below that. We don't care. We don't know that text data is being broken down into ASCII bits. We don't care. We don't know that those ASCII bits are being broken down into binary. We're abstracted from that. We're 2 layers, 3 layers, multiple layers on top of that. We don't care. We just send a text message and it works. We don't know. We're not interested. We don't care about what's going on in the background there. So that is abstraction. So abstraction lets us hide the details and instead focus on the problems at a higher level. So what problem were we trying to solve today? So we were trying to solve representing text. And then what detail from the last few lessons was hidden or out of focus? Well, you think the last few lessons that we did, we go back to Google Classroom for a second. So we did overflow and rounding, so the large and small numbers. We did binary numbers, so we introduced you to binary numbers. We did a circle square patterns, which was the precursor to binary numbers. So going back to here, what details from the last few lessons was hidden or out of focus? Basically, you know, we the binary, all the binary, the conversion of the binary to text, all of that is abstracted from us when we're using a phone to send a text message, when we're using when a computer to send an email, when we're using Microsoft Word to write an essay. That's all abstracted from us. We don't care about what's going on under the scenes. We're just using the product for what it's supposed to do. So we're being hidden, the low level details of text representation are being hidden from us. And obviously spelled that wrong, doesn't like it, that's definitely hidden. So going back to a diagram here, we got a text, we've got a ASCII, we've got a binary. All we were interested in here is the text. And our final slide today. So what is another example of abstraction in your everyday life? So something where you don't completely understand how it works, but you can still use it with confidence. So go ahead and take a couple of minutes and have a think about that and enter into your student deck something. For me, I'm going to say, I was going to say driving, but I think, the internal combustion engine, I think pretty much it's relatively straightforward how that works. I'm going to say how my remote control works to turn on and off my TV. So we're abstracted from the fact that we have an RF transmitter in there that transmits a stream of, well, we're going to say binary data. It has to be binary data because electronics only use binary. So when I push a button, there must be some binary representation of the button that I'm pushing, which is very similar to what we've been doing today, representing the text. Okay, well, that is the end of today's lesson. Hopefully you enjoyed it and found it interesting. I will speak to you again at our next lesson. Now have a good day and thanks for joining.